So, what was difficult, what was a little frustrating when you guys were taking notes on Friday of the polar equations? Drawing the circle and circle and circle and circle. Years past, I've done like total handouts. Probably I'll do it for pre-cal. They can like paste it in their notes like they did the unit circle, and then they can make it all pretty and gorgeous. But here's the point. Polar comes back in Calc BC, and maybe you guys will get there. We don't want to be making those circles, and they're not going to give us those circles. So we have to be able to deal with polar without the circles, but still maintaining the integrity. Ooh, what's that mean? Maintaining the integrity. Kind of. While still keeping the meaning, while still holding to the truth, we could say, using Melanie's words, of polar graphing. Because polar graphing, when R is used, R is a radius, we're supposed to be moving circularly, right? So for example, on Friday when we were trying to graph, I don't know, let's see, what point? When we were graphing, I guess 530 degrees, it's kind of lame. I would rather do something like negative 5, 150. Yeah, when we were graphing negative 5, 150, how did we graph this point? What was the first thing that we did? We went to 150. So in a sense, you can have a little person, you can like twist them until they're facing 150. Does that make sense? So it's not that we're out here on 150, we're actually on the inside, and we're just twisting until we're looking at 150. But then what do we have to ask ourselves? When we look at the negative 5, either we're going towards or away. So what were we doing with negative 5? Away. Now here's the dilemma. If we're going away, we're going back towards 330. We talked about how it's the same thing as turning towards 330 and going positive 5. They're the exact same point. But here's a dilemma. As soon as we change the graph to something like this, how do you think positive and negative on one of these guys? Yeah, to the left, to the right. To the right will be positive, to the left will be negative. Up, down. Up will be positive, down will be negative. Is that very different than positive and negative radii over here? Yeah. Because whatever angle you're on, 60, positive you'll be going towards, negative away. But then if you go down here to 240, positive you'll be going the same direction that you were going negatively a second ago. It all depends on the angle. So we're going to have to do a few things when we come here. One of them that we're going to have to battle is the positive-negative idea, and the second one is going to be the rotation idea. Because if we were supposed to, for instance, on letter D, go 5. Yes, I know we're going back 5 tick marks, 1, 2, 3, 4, 5. But here's the struggle. Can we see these diagonal circular tick marks when you're here? No. So how do we think about it? This one's easy because what's the angle for 7, 0? And that's going to be on what we would call the polar axis. And we would go out 7. 1, 2, 3, 4, 5, 6, 7. I think 7 is my last point. Let me double check. 1, 2, 3, 4, 5, 6. Ooh, no, it's not. Okay. 7's now here. That one's easy because it was on the axis. I could use the tick marks on the axis. But it gets hard as soon as I look at 3 pi over 4. So what angle is 3 pi over 4? The next point. 45. Good. So 45 degrees. Could I approximate 45 degrees? Yeah. Why do you think I went all the way across? Good. It might be negative, and if it's not negative now, maybe I'll end up over here anyway in just a little bit. Does that make sense? So if I make it in one nice fluid line, well, I have a higher probability of making it straight. So I have my 45. That's not too bad because we know our unit circle, but the dilemma is the 3. So do I go over 3? Up 3? No. I go circularly 3. Now the struggle is, see how my tick marks are squished and then more elongated? What's this kind of similar to? The calculator. Because the calculator, isn't Zoom standard a 10 by 10? And haven't we talked about since the beginning of the year that that screen is a rectangle, and so therefore the x's are squished a little bit and the y's are elongated a little bit? But if this was perfect, wouldn't this technically be a little circle? A little quarter circle? So if I connect the 3 with the 3, if I rotate from one 3 to the other 3, the horizontal to the vertical, wherever that intersects my angle needs to be my point. Does that kind of make sense? So my A is the 0.70, my B is the 0.3 pi over 4. I have my A out here, I have my B right here. What am I going to do for C? The angle is pi over 2, so the angle is my y-axis, right? 90 degrees? But I'm going 0 out, so yeah, where am I staying? Right here in the center. Right here in the center. Does that make sense? You guys have ever used Google Maps and you can like go to the street view and then you have like the little person or the little dot and you can like rotate it? That's kind of what's going on right here at the pole. And it only ventures out if it has a radius. If it doesn't have a radius, you're stuck right there. So that's going to be my letter C. How about D? Okay, so the angle, 2 pi over 3, that's going to be second quadrant. 60 degree reference angle, which will be 120. So I'm going to go ahead and do one that's a little bit steeper. I'm going to do it all the way down just in case. Is it especially good I went all the way down? Because? So instead of going out 1, 2, 3, I'm going to go back 1 if you want to think about it, 2, 3. Oh, sorry, I was looking at this one. Thanks, Colby. I only have to go -1, so I connect the -1 with the 1. It doesn't matter the signs. The negative is me going backwards. All I'm thinking now is the 1 that connects with the 1. The vertical one with the horizontal one. Remember, you have to rotate. This is circular. Polar is built on circles. But where the 1 intersects, booyah, there's D. Sorry, C just kind of got stuck in there. I don't know if I can get him out, though. Can I get you out? Nope. 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 I'm not even going to try. Anyway, C is the pole, and then D is that one. Who do I have now? E? Ooh, now what? Positive x-axis, so the polar axis, this direction. Because pi is over here. So I'm facing this direction, but I'm backing up. So 1, 2, 3. So there's my E. F is the 0.03 pi over 2. Oh, where am I again? Yeah, I'm back at the origin. Or remember, what's the name for the origin in polar? The pole. The pole. I mean, you can think of it as the center, right? But it's the pole. You guys are having way too much fun with that with the flat earth thing on Friday. Just to help you remember. G. Now I'm at 7 pi over 4. So I'm over here. No, where's my pi over 4? 1 pi over 4, 3 pi over 4, 5 pi over 4. Aw, stink. I need my 7 pi over 4. So let me get him. There he is. 3, I'm going to be going out 3. There's my 1, there's my 2, here's my 3. Here's where it intersects approximately with 7 pi over 4. That's going to be my G. And then, oh, where am I at H? Same spot as we started. Does this feel at all like we've kind of gone in a loop? Because we ended where we started. We were kind of like rotating as we were going. It might feel like we went into a loop because we kind of did go in a loop. The only dilemma is, what loop did we go in? Now, a lot of you don't have tons of feel for polar graphs and how to connect points. Some of you might do something crazy if I said, okay, connect the points in order. You're like, okay, cool. So I have this, and then I had that, and then we had the 0, 1, and then we had this one, and then we have that one, then we had a 0, 1, then we had that one, and then we went back. And we're like, ooh, it's like a arrowhead? I don't know. Something or other. It's like a kite. It looks very pointed. It looks very linear. It looks very rectangular. But here's the problem. What's polar supposed to be built on? Circles. I wonder if we were to plug in non-unit circle values, like pi over 5. That's awkward, but we could have done it if we had a function. Or maybe there's something going on in between here, like maybe pi over 6, pi over 3. We didn't do like a pi over 4 right here. That might have been nice. 3 pi over 4, 5 pi over 6. What if I'd given you more points of this function? And here's the struggle. I need to figure out what this function is. I didn't actually write an equation for it. But I also didn't want you just going to your graphing calculators to graph it. We could call this r is equal to, give me a second. Eileen, maybe you could help me on this. It's symmetric about the polar axis, which means positive theta or negative theta is the exact same, which would be cosine. Cosine of 0 is 1. 7 cosine of theta. But then I need pi when cosine is negative 1. Nope. Does that work? Not perfectly, but it's close. So it'll give you enough of an idea. Hold on, double checking. This will match up with like half the points. I made it a little bit too nasty, making it 7 pi over 4. I should have made it a little bit grosser, but I was trying to make it easier numbers for you guys to graph. Go ahead and graph this in your graphing calculator. We'll say that, bless you, we'll say this is close to, beep, beep, beep. In order to fit into this equation, basically these ones are the pi over 4s, because cosine of pi over 4 is root 2 over 2. It's going to be nasty and decimally, so it's not going to be perfect. But guys, in polar mode, go ahead and graph. It's close to this, just to give you a feel for what's going on. It's close to 10 cosine theta minus 3. Colby. Weird, right? Totally weird. Because whenever we think about points, we always think about x's and y's, where the x is the independent, right? And the y is the dependent, where y is equal to f of x. But that's going to be very, very, very different from polar, because polar, theta is the independent. You're totally right. R is the dependent. And we're going to write our functions, r equals f of theta. So you can think about the dependent and the independent are switched. The dependent and the independent are switched. Okay, so you guys are supposed to be in polar mode. If I were you, I would go back and change the graph to the little circle with the line. I think it'll be helpful in polar mode. Based on my experience, just trust me. For right now, 10 cosine of theta minus 3. And I want you, in whatever mode, window, zoom, whatever, just hit graph. Don't even think about it. Just hit graph. Woo-hoo-hoo! What is mine doing? Is mine cooler than yours? Oh man, mine's still going. And it's still going. Now here's the crazy thing. Even with my really messed up window, pause. I want you to look at what this craziness seems to be converging to right here on the inside. And does that look kind of like what you guys have? Huh. Now, pause. Pause. What's wrong? I want you guys to see my mode. What mode am I in? Radians or degrees? Radians. Check your mode. Are you in radians? Okay. I want you guys to go to the window. And I'm going between 0 and 360. Are you going between 0 and 360? Why does it not make sense for me to be going between 0 and 360 with steps of 5 if my mode is radian? Why does this not make sense? And why is my graph, even though it's cool, why is it not looking like it should? Because what the graph should look like is as you spin, and if we were to have more angles, you would end up spinning in, coming out, spinning in again, and coming out. It's all a rotation. You don't connect with lines. You don't connect with lines. You connect with curves. Not that lines are impossible to ever get in polar mode. You can get lines in polar mode, but it's very rare. It's very rare in polar functions because it's all built on thetas, and thetas, think sine and cosine, aren't they cyclic? Aren't they periodic? Don't they go in and out and up and down and between 1 and -1, smaller values, larger values? So in a sense, our shapes are going to be expanding and condensing depending on the trig values. Joseph, can you just check what he put into his y equals? Now pause, come back. Guys, I haven't actually told you what zoom you should be in. Pause. I know it's exciting, but coming back. All I've told you so far, all I've told you so far is I'm in radians, and this 0 to 360 with steps of 5 is bad. What would happen if I changed my zoom to zoom standard? Because I didn't hit any buttons, I just went straight because I had actually set up my graphing calculator to be messed up on Friday. So, if I do zoom standard, oh. Hey, look, it looks an awful lot like what I drew, right? Huh. It is a little stretched. I mean, we can make the window, if we want, we can make the window go a little bit more to the right by changing our x max, right? We could go to like 20 instead, if that helps. You can see it maybe a little bit better. Why is it going so far out? Remember I said this is close to, it's not exactly ours, because ours would have had decimals in lots of places if I had done it like based on an actual function. So it's close to ours, not exactly, but do you guys see how this shape can happen in polar? Now ours, the dimensions are a little bit different because it's not this true function. This true function, to be honest, would go out to 13. It would go out to 7, but it would also go out to 13. So it goes out 7 at first, and then as soon as cosine is -1, it'll go to -13, which is why you see this bigger circle than ours. So maybe, Carl, you just couldn't see the bigger circle because you were zoomed in. That's very possible. However, hold on. This looks very different than the one I just had, right? Okay, so what was so different? What is my window now? I hit zoom standard. I didn't do anything. The calculator said, okay, I'll make it right. What did it make the theta min to theta max? 0 to 6.28, da-da-da-da-da. Wait, 6.28, da-da-da-da-da. What is that? 2 pi. Why would it be going to 2 pi if I'm in radian mode? Oh, I was going to 360. That's more of a degree measurement. Now here's one more thing to think about. Remember how we were talking about parametric and about how if you check in more often, right, with the moms and then the GPS and all that jazz, if you check in more often, you'll have more of an idea of what's going on. Guys, if I'm in radian mode, isn't sine and cosine, aren't they going to finish one full cycle in 2 pi and 6.28? Right? It'll finish one full cycle, the full unit circle, all the different values in 6.28-ish, right? So if I take a step of 5, what have I just missed most of? If I'm going t steps or theta steps, I missed basically all of it. Because if I take one step, I'm like, great, I can see one thing, but then one more step and I'm out of that entire cycle. I'm in a new cycle. One more step, I'm in an entire other cycle, and in these weird spots too. Not even the same spots. So I had it graphing for a long time, 0 to 360, but it was picking super random, I mean it was every 5, but super random in context of radians, super random spots. Now if I'm going between 0 and 6.28, taking a lot of little baby steps in there by 0.1s, well now I'll get a really good picture of what's going on. And if I had been in degree mode, where my angles were measured very differently, If I was in degree mode, radian measurements won't work well at all because radian, I'm barely covering any of that cycle of 0 to 360. So if I did try to graph this, I would see stuff, but it wouldn't be very much stuff. Why? Because there's 360 to cover, and I just said only do 6.28 of it, and by the way, take all these baby steps, but it just went like, done. So I would need to do zoom standard again. Hey, zoom standard's nice, right? For the window to be like, oh, you want degrees? Okay, I'll help with that. And I'll make it what you should put your window as. 0 to 360 with steps of 7 or 5 or 3 or 10 or whatever is going to give you a better picture. So we have this new theta min, theta max, theta step. Like with parametric, we had the new T min, T max, T step. Because, just like with parametric, x and y are dependent on t. In this one, the x's and y's, which the calculator does, I mean, we wouldn't really do it, but the calculator does. You can get x's and y's in terms of theta. Because it's still graphing on an xy Cartesian system. So it's actually, what it's doing is it's converting the r's and thetas into x's and y's and then actually graphing x's and y's. What we're doing is we're using an x and y axis and still thinking r's and thetas as we graph because it's so much easier and so much less work. And we're going to see the work today as to how to go from x's, y's to r's and thetas and how to convert backwards. But I want you guys to try one more thing. Do you know how in polar, what am I in right now? Degrees? That's fine. The answers will be nicer. If you want to get in degrees too, go mode, go degree mode, then do zoom standard. Make your window all nice and pretty and neat as to what you want it to do. Do you guys remember how in function mode there's all these cool options of intersections and maximums and minimums and zeros and all that stuff? What menu is that? Second trace. Yay, we can find all that stuff for this too. When you change modes, your second trace, your calc menu changes also. It's not as possible to do all those functions that you used to be able to do with maximums and minimums and zeros. We can still do values. This is technically calculus, the derivative of y with respect to x, the derivative with r with respect to theta. But long story short, nothing that we're doing right now. Value, okay, the one that we can do. What's that? Yay, value. Oh, it asks for theta. That makes sense because as Colby and I were just talking, theta is the independent variable like x used to be for function mode. So let's put in something like, well, remember I said that mine was probably all far off. That's okay. Let's figure out what is going on at 45 degrees and why my function doesn't work. So at 45 degrees, because I'm in degree mode, oh wait, it gives me an x and y. I wanted to see r. It gives me an x and y. I wanted to see r. We'll get back to how the calculator can tell us r in just a second, but for right now, didn't we take another page of notes right after this? And wasn't there a triangle? Why was there a triangle? I want you to think about 45 degrees. This is the one that I have my calculator on currently, right here. I have it on this point, or at least a similar point. I'm trying to figure out how far off my graph is, because obviously it's pretty far off. My biggest one is 7, and for that one, the littlest one is 7. It goes out to something crazy like 13. What could have made this a better graph? If I had... I'm trying to see if I could have even fit it to the data. I could have fit it a little bit better, but that's okay. If I'm trying to figure out how to compare what this one is to this one, we're trying to look at pi over 4 and see how far off we are. Polar would say, oh yeah, no big deal. That's 45 degrees, turn 45 and go out 3. That's what polar would say. But what would rectangular say? Well, hold on. Polar would say, turn an angle, go out an r. Polar would say, turn an angle and go out an r. From the center, from the pole, turn an angle, go out an r. That's what polar would say. But what would x, y say? How would go over x and up y? Have we seen this triangle before or something super similar? Well, A, it's a right triangle. But B, if we ever had to go from x's and y's to hypotenuses and thetas? Vectors? Magnitude and direction versus component form? Now, don't stress, these aren't vectors, but the math is exactly the same because it's the same right triangle. Very, 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 very different context, except that motion can happen on never mind. You can kind of apply it once you get to BC. But for right now, very, 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 very different. But we can say, well, if we want to get back to xy, or if, like at the calculator, it gives me xy, and I'm curious about the r theta, can I handle that? And the question is, the answer is yes. Why? Because it's a right triangle. Horizontal, vertical always hits each other at a right triangle. So we can use, now guys, I'm not going to say which is which. I'm just going to say, hey, all these formulas can be helpful. It just depends on what you're doing as to which ones you're going to use. So for instance, you can say, hey, if I have x's and y's, those are sides, I can get to r with the Pythagorean theorem. If you have something like, hey, I have x's and y's, I can get to tangent because y over x, the ratio would be opposite over adjacent. Sure, we could go cotangent, adjacent over opposite, but who really wants to choose cotangent instead of tangent? Not me. So we could also say theta is going to come from PS. This is not an equals, this is a colon. This is not an equals, this is a colon. But theta can come from using tangent inverse of y over x. We've learned by now, whenever we use tangent inverse, we always have to consider the picture, consider where we actually need it. Like with angle of inclination. This was my example for pre-calc, so I try to make things a little more visual for them. For pre-calc, angle of inclination, section 10.1 lines, m equals tangent of theta. This was in the beginning of chapter 10. Angle of inclination, what is the angle to a certain line? So downhill slope, anytime you plug in downhill slope, a negative slope for tangent inverse, you're always going to get a negative angle. So here I am, looking at a mountain. It's downhill as far as, well, looking at it left to right. It's downhill. Has a negative slope. Plug it in my calculator, if I can measure the up and the over to the mountain somehow. Which I could go up and then have someone like, so the up and over to the mountain. Okay. Calculator spits out a negative angle. Wait, where's the negative angle put me? At the mountain? Doesn't it put me in the ground? Now, if I eventually follow it, thanks Jack, it would be in the core of the earth, Jacob, for you at the end. However, the negative angle, I'd have to dig a hole to check it and be like, hey, does it work? I don't want to dig a hole, I want to look at the mountain. So instead of taking the negative angle, I have to add 180 to get to the positive angle. So same thing here. Sometimes when you do tangent inverse, it'll put you in the wrong quadrant. Maybe you have to add 180, add pi to make it right, but there you go. We could also do something like we saw with vectors. X, which is adjacent, could be r hypotenuse times cosine of theta. It's a rearrangement of ca. Cosine equals adjacent over hypotenuse. Solve for the adjacent, we get this. We could also do the same thing with y. You guys saw this in vectors. It's a variation of so. Sine equals opposite over hypotenuse, move the hypotenuse. So all of these formulas could be good. How do we know which ones to use? Well, let's get some examples. What if it says, convert, coordinate conversions. Convert from polar to rectangular. P.S. Pretty sure the quiz is going to be on Thursday. Convert. Focus. How do I go from polar to rectangular? Wait, they just told me what kind of point is this? Based on directions. Who's this? Yeah. So if he's polar, then what does that mean negative 3 is? And 11 pi over 6 is going to be theta. So how do I get to x's and y's given r's and thetas? Oh, come find a formula that says, give me r's and thetas, ooh, and I'll give you an x. Give me r's and thetas and I'll give you a y. So we can say, oh, it's easy to get to rectangular. They want me to get to x and y. I say, sure, I can do that because x is just going to be r times cosine of 11 pi over 6. And y is just going to equal negative 3 sine of 11 pi over 6. And just because they were super nice and gave us a unit circle-y one that we do not need our calculator for, 11 pi over 6, 30-degree reference angle in the 4th quadrant. Over a lot, down a little, over a lot, that's going to be negative 3 root 3 over 2. y is going to equal down a little. That's negative 1/2. Negative 1/2 times negative 3 is positive 3/2. I can get to my point and say, oh, no problem. Negative 3 root 3 over 2 3/2. Or if I was going from rectangular to polar, I could see this guy as an x and a y trying to get to an r and a theta and say, do I have formulas that say, give me x's, give me your y's, and I'll give you an r? Yeah. Pythagorean theorem. Negative rad 3. Negative was in the wrong spot. Squared plus rad 3 squared equals r squared. Isn't that just going to be 3 plus 3 is 6? So is an r just going to equal the square root of 6? Ooh, plus or minus? But it's okay. If r is a radius, we could go positive out that radius, so like towards angles, or negative out that radius, away from angles. That kind of makes sense. And then if I was to do theta, I could use this formula that says, give me your x's, give me your y's, and I'll give you a theta. So we can use tangent inverse of y. Guys, it's going to be like the inclination. It's going to be like the downhill. We don't want to go digging a hole in the ground. This one's going to give us a negative angle. Wait, this is just tangent inverse of negative 1. That's a 45 degree, but this is technically going to give me negative 45 degrees. Wait a minute. This is fourth quadrant according to just tangent inverse spits out angles between negative 90 and 90, but where's this point? Wouldn't you go negative root 3 over 2, positive root 3 over 2, and be in the second quadrant? So how do I get to the negative positive second quadrant if I have the fourth quadrant? I say, oh, I want the 45 for theta to be in the second quadrant. But here's the kicker. Are you ready? Could you have chosen positive root 6 with 135 to get to this point? Yes. Pause. Couldn't you also have chosen negative rad 6 from negative 45 and had the exact same point? And couldn't you have made infinitely many other points? As long as it's one that works, I don't care. All right, cool kids. Get started on 10-7. You guys are going to be late, though, and I'm not going to write you a pass. So if you want to stay, you won't get a pass, but if you want to stay. Eileen, let me have the test, please. Thank you. I have Jacob's. I have Melanie's. I have Ryan's. Ryan Boda. I have Caro's. I have Andrew. Struggle. Jacob. I have Andrew. If you want it, come get it. I have Kevin. I have Dean if he wants it. I have Caroline if she wants it. Oh, Melanie. Dean. Andrew. Melanie. I have Joseph if he wants it. Melanie, make sure you only have one. Rebecca, if you want it. Can I have the other one? Thanks. I have Victor's if you want it. I have Ryan Nix, but I think he already left. I have Jack, but I think he already left. I have Becca. Oh, I think she already left. I have Toby. Yes, thank you. David. I have Janelle. I have Thomas. I have Patricia. I got that at the bottom. I have John. I have Colby. There you go.